a very good afternoon to everyone. Yeah. So first of all, I can introduce myself, and then we start our today's lecture. So I am Dr. Vijesh Patel. I am a postdoctoral researcher at Department of Mechanical Engineering under Professor Robotics and Design Automation Laboratory. I was also an associate professor in India. I worked on drones, robots, industrial aerodynamics, that is design of vehicles, airflow through vehicles, and something about wind turbines. I work on several biocomposite hybrid materials. Also, I was in entrepreneurship. I was head of the entrepreneurship cell of my university there. So it was about myself. So today's lecture is just a casual lecture on how the robotics is rising from past to future, where we are, and I will share some concepts about new future trends. So today's title is Progress, Challenges, Prospects of Future Robotics and its Applications. So we'll see some of the videos and try to learn what's going on in the world about robotics and what is the future of that. So today's outline of the presentations, we go from the bottom, that is rise of the robotics, and then we classify which are the types of robots, how to classify it. Then I'll share something about telemetry and tele-robotics. Then we come to micro-robotics. These are small, I cannot completely go through all the classification in one class. So I have selected like 3 or 4 steps like telemetry, micro-robotics, space, soft robotics. It's generalized with soft robotics, but I include space on it, how the space application for soft robotics can be done. Then robotics with large language model, it's the future. Then what is robotic transformers? I don't have about the transformers in movies, but what is robotic transformers in digital age? So we'll learn about this, we'll see that what's going on in the world. So this is the outline of today's presentation. Let's come to rise of the robotics. First of all, how the robot term comes. Like in 1920, it was first used by Czech author Karl Capek. They used the robot in his novel, and this was a picture which he portrayed. So he has never think that what's going to be the next. So he has just portrayed the term robot in his first author. Then comes to that. I've never talked about like what's the previously what has been done in the past, but it started from 1920 where this robot was termed. Then comes to the 1939 where the first demonstration has been done in the World Fair, World of Tomorrow in New York City, named as Electro, a humanoid robot which can enjoy while taking a job.
I know you enjoy these, and I'm really going to try to give you a nice flight out these. So here you are. You got that?
So the robot is we joke with
You?
right now holding a cigarette.
This? Cigarette? Go on. Oh, yes, electric. It would be right, you go. Oh, here you are. And that's he's only 2 years old.
So in this World Fair, they introduce Electro as a robot which teaches, which blows a cigarette by cracking a joke. So, but we teach them a bad habit first, than the good habits. So then 1941, Sir Isaac Asimov formulated 3 laws of robotics, which are very important for humans. Like a robot may not injure a human being, or through inaction allows a human being to come to harm. A robot must obey orders given in by human beings except where such orders would conflict the first law. Third, a robot must protect its own existence as long as protection does not conflict the first and second law. So these are the three laws in 1941 Sir Asimov formulated. These are the three laws of robotics. Then in 1948 Sir William Gray created first electronic autonomous robot which three machine mechanicals spectronics.
When light strikes the sample, driving and steering mechanism sends a ray towards it. If she brushes against any object in her path, contacts are operated that turn the steering away, and so automatically she takes avoiding action.
So we were the first autonomous robot which was made in 1948.
He works in exactly the same way.
How they demonstrated
full cell nervous system. And then with more cells, they were able to do many more tricks. Already Elsie.
So that was the autonomous robot developed by William Gray. Then comes to 1950s where the word intelligence comes into existence in a paper called Computing Machinery and Intelligence, where they make a tuning test demonstration where the experiment was an interrogator which write down two questions and send to a machine and send to a human. And they analysis this, so this is called a tuning test, which comes in 1950. Then 1958, Biggs introduced microprogramming on small machine, is that. Then comes 1954, where George Devil invented a 6 degrees of freedom robotic arm capable of sorting digital commands, which later became Unimate Industrial Robot. In 1956, he co-founded Unimation, the world's first robotic company, with Joseph.
A robot for industry. And this is it, Unimate, a machine that can reach up to 7 feet and perform a multitude of tasks in the factory or laboratory as skillfully as a man, but without getting tired. It's controlled by a built-in memory system. You just lead it once through the required motions, and it can then repeat them 24 hours a day, week after week. It can position objects to within 50 thousandths of an inch. Completely unaffected by heat, cold, fumes, or dust, it could take over a lot of unpleasant jobs. It can operate unattended for 500 hours. Originally developed in the States, it's now being made in Britain, and this was its public debut. Have one with me.
So it was our first 6-axis robotic arm, which was known as Unimate. Then in 1956, the Diamond Summer Research Project, they have a conference in Denmark. So it was like this project they have introduced for artificial intelligence as a field. That this year comes, artificial intelligence comes into existence in all the curriculum as a field of research. Then comes to 1960, Frank Robles developed the first perceptron. It's a neural network, basic of neural network. So in 1960s, it marked a significant milestone in the field of artificial intelligence. The perceptron, a simple neural network model, introduced the concept of computer learning. Then in 1961, Unimate, which was developed in 1954, comes into existence through a large industrial of the Motors plant. And in 1968, Stanford Research Institute Artificial Intelligence Center developed the world's first mobile intelligent robot. It was known as Shaky.
Shaky was the world's first mobile intelligent robot, embodying numerous breakthroughs in artificial intelligence, robotics, computer vision, navigation, and other research areas. The robot was developed from 1966 to 1972 by SRI International, then called Stanford Research Institute, and its legacy and impact are still very much alive today.
Shaky is really the great-grandfather of things like self-driving cars and even military drones. The hardware was really pretty primitive, but the software architecture and the software algorithms are what changed the world.
I think we all thought we were doing really interesting stuff, so it didn't really dawn on us that we were doing anything special.
Shaky established a position about what we should be thinking about as possible, as feasible.
To understand why Shaky is so important, we have to go back to 1966, and we have to understand where AI research was at that time.
Well, you have to remember that it was pretty much of a greenfield when Shaky started. All over the country, and even outside of the United States, people were beginning to build the components of artificial intelligence.
So after developing Perceptron, this 1968 Stanford Research Institute used that one for the development of the autonomous intelligent robot called Shaky. In 1972, Fiat in Italy and Nissan installed the spot welding robots. Then comes to 1974, which we see is right now, it's like a robot with microcomputer controlled industrial robot called as Cincinnati, developed by Cincinnati, and it was called as T3. The picture here is a T3, which is a mini computer controlled industrial robot, comes into existence in 1974. In 1976, the robot arms are used in the first SpaceX project, called as the Viking 1 and 2 space probes. Then 1979, Hiroshi Makino, University of Chemistry, Japan, developed the SCARA, which still we are using the SCARA-based robot for a single compliance assembly robot arm. In 1980, the University of Rhode Island bin picking robotic system demonstrated for picking of parts of in random orientation and positions out of a bin. In 1984, Joseph Anadol founded Translation Robotics to develop service robots primarily for medical industry. So this is the picture where we can see that the various service robots which used for medical industry was introduced by Joseph in 1984. So this is a journey beginning from a word robot in a novel to this stage. Then 1984, ABB Sweden produced the fastest assembly robot IRB 1000. In 1985, BPL Research founded a company by Joner, who is often regarded as a personal point of term of virtual reality, like VR headsets they introduced in 1985 by BPL Research. Then 1996, Honda developed E0, the first series of humanoid robot. It walks in a straight line on 2 feet. See the first robot E0, how slow it is working on 2 feet. In 1988, Jabberwocky AI chatbot was created by developer Robo Carpenter. It aims to simulate a natural human conservation in an entertainment way. If you want to try, you can try this website. It's still working. It's jabberwocky.com. You can just try and play it with. You can send something. It will react. It will give you answers. This is still working. So this project was started in 1988. It was the first AI chatbot. 1988, the first helpmate service robot begins in Danbury Hospital. So this was the first helpmate robot, like the robots which are earlier made in 1984 by Joseph. which was installed in 1988 to the first hospital is Danbury Hospital. In 1990, iRobot Corporation founded MIT Robotics to introduce domestic and military robots. 96, KUKA Germany launched its first PC robot control system. Then 1997, Pathfinder for Mars was launched. It was an autonomous vehicle. In 1998, ABB Sweden developed the first flex speaker, the world's fastest speaking robot, based on the Delta robot developed by Raymond Carver, Federal Institute of Technology. So this was the Delta robot which was introduced by ABB Sweden. So initially, it was just every year we are going to demonstrate a new technology in the past years. Then in 1999, the first remote diagnostics for robot via internet was demonstrated by KUKA. Then initially, the surgical commercialization, the famous Da Vinci surgical robot was introduced in 1999. This Da Vinci surgical robot, still we are using it for, it was a genius for surgical, as a surgical robot. In 2003, RoboCoaster, the first entertainment robot based on articulated robot by KUKA. In 2005, driverless car by Stanford University and DARPA Grand Challenge. They win the DARPA Grand Challenge as a one for with a driverless car. Kiva system also presents BU 1000 warehouse logistics. So in 2005, the robotics application comes into logistics. 2006, KUKA Germany presented the first lightweight robot. It's a robotic arm which is the lightest of all the robots in that category. In 2007, KUKA Germany launched its first long-range robot with heavy-duty payload of 1000 kg. In 2007, the race begins for heavy-duty robots because the industry, the car manufacturers, everyone wants the big robots to help them in the scale version. So all these robotic companies was going to like heavy robots. So KUKA launched its first 1000 kg robot. Then 2006, the KUKA and Fanuc were the two big companies in the robotic in that era. Still, they are the big companies in the robotic world. So in industrial robots especially. In 2008, Fanuc Japan launched a new heavy-duty robot with almost 1200 kgs, more than KUKA. Then in 2009, the release of first ROS, which we know as Robot Operating System, an open source collection of software intended to reduce the programming effort and propel the development of robot applications. Then in the same year, Cyberdyne launches its first powered exoskeleton to support paraplegics. In 2011, a Robonaut R2B launches its first international space station. R2 is the first humanoid robot in the space. So in 2011, we launched as a humanoid robot which goes to the space. In 2011, ABB launched its first collaborative robot UAV designed for small part assemblies and electronics. 2013, Boston Dynamics introduced Atlas, a humanoid robot capable of walking in uneven terrain performance rescue missions. Then in 2015, it comes to the era of social robotics. Then SoftBank introduced Pepper, its first humanoid social robot, with ability to recognize faces, became human emotions through analyzing facial expressions and tone of voice.
What's only 4 feet tall, weighs just 62 pounds, but is filled with endless possibilities? Pepper. Join the movement to enhance and elevate Pepper, the emotional humanoid robot built to benefit mankind. This is Pepper today. Where will you take Pepper tomorrow? Visit developer.softbankrobotics.com.
It was a Pepper, which was a social robot which introduced by the SoftBank. And then in 2016, NVIDIA introduced its Jetson TX2 platform for making AI-driven edge computing in robotics, which is more accessible. From 2016, I was supposed to put some slides, but I think here, every day, every month, there is a new discovery comes into robotics. So it was just entered into transformative era, expanding from drones in logistics and surveillance to underwater robotics for deep sea exploration, space missions, medical innovations like robotic surgeries, social, entertainment, and many more. So I put the signature of infinity because it's going on. Nobody is stopping. So it starts from a robot world to current which we are. So you can think how this age has been transforming and how it is going through a scalable way. So next is the classification of robots, like how we can classify it. So I have made it like classification in different ways. Like we can classify the robots by functionality. If you classify the robots by functionality means you have a service robots, which is into service like cleaning, you are helping in your house or something, which gives you a service to a personal or in the official one. Then comes to the mobile robots, which can be related to two-wheel robot or which can be moved autonomously or on bed. So these are the mobile robots using logistics. And then comes to industrial robot. These are based on the functionality, what functions it does. So it's based on industry, which is used in the heavy industries. So it was industrial robots. Then comes to the humanoid robots. It's like a human appearance. The appearance with the humans and human actions. It can do the human functions. Like what we can pick up a glass, we can talk to someone. So these are the category of humanoid robots. Then comes to the autonomous robots, which can move autonomously without any human interventions or maybe human movement. So mobile robots and mobile robots may be intervened. You can use joystick to control it. But autonomous robot can be done autonomously. Then comes to aerial robots. So it's the name itself. It can fly and it can move in the air. Which are the aerial robotics. So these are based on the functionality. Then by applications. The classification of robots can be done by applications, like in medical. It's a generative robots. You can see the Da Vinci robotic systems that we use in the medical robots. Comes to the agriculture robots, so which only specify the application related to agriculture for picking up of the fruits or for spraying of the pesticides. It's generalized in agriculture. Then comes to military robots, where it's used for defense purposes and the military purposes. Then comes to the exploration robots, which is used for space exploration or underwater sea exploration. And then the entertainment robots. Yeah. You can play with some robotic games with joystick. You can play something. We can ask some questions, answers, or maybe for entertainment purpose. So these are the categories of classification of robots by application. Then classification by design. These are the stationary robots, which is fixed into one place for variable tasks. Then comes to bio-inspired mobile robots, which we inspired to the nature, the movement of nature, like snake or like any of the animals, like cheetah or somewhere. If you inspired from like a dog, if you inspired and you make some robot, it's a robot with inspired by design. Then comes to the swarm robotics. This we learn from the swarming of like bees or swarming of ants, because they move in a line. So it comes by design from this related to swarming, a behavior of various animals or insects from which is by Mother Nature. So if you see in the Mother Nature, there are lots of examples are there which we can adopt to find a solution for some problems in the real world. So it gives you an example. If you can integrate that examples into for the solution to the real world, it can be by design. So it's like a swarm robotics. Then comes to modular robotics, which are very flexible and which are regenerative, reconfigurative. Like you can, it is like a snake, but it may be individually also it can be used. So it's a reconfigurable place like modular robotics. You can attach, deattach, make 3 parts or make 2 parts from one robot. So it comes by design. Then comes to the soft robotics. This is a new era where we need something with the soft materials. Soft robotics is developed as the material installation of the material are developing. Day by day, new materials are coming into existence which can be used for some of the applications. Then classified by control, like manual control robots which can control through humans. Then comes to autonomous robots. It's the classification may collide with other classifications, but yeah, I have made it like in this, like we can say that it can be classified as by controls. Autonomous controls, then teleoperated robots. Like there are robots which can be worked in some of the hazardous environment where human beings cannot be go. So this where we can use, like we are sitting in some other place where we are safe, and the robots are installed in such a place where there is it's a hazardous place where it's not good for the humans. So we can use telerobotics into that. So in today's lecture, we will introduce the telerobotics and telemetry. Then behavior-based robots. So these behavior-based robots are like from nature of we imitate some of the behaviors of animals or some of the living beings or some trees or something, and for that behavior, if you adapt in some robots or design a new robot, it's called the behavior-based robots. Then AI-controlled robots, which is controlled by the AI-based algorithms. Then comes to the classification by environment, where we use this, which environment it can be used, like aerial robots, it can fly in the air. Space robots will be used for in the space explorations above the Earth. Then comes to amphibious robots, which can be used in the land, water, together. Comes to the underwater robots, which use in the deep sea explorations. Then indoor robots, which only used for the indoor applications. Then comes to hazardous robots, which used for the hazardous places. So these are classification of robots by environment. So this we classify robots into functionality, application, design, control, environment. So these are the classification of robots which we have in today's scenario. Now comes to telemetry robotics or telerobotics. What is telemetry and telerobotics? Let's see a video and then we can see that what actually is telerobotics and how it can help human beings. So what we have seen in this video, it's a specially able person. From current scenario, we doesn't resemble if a person is not a able person. What we demonstrate is it's a disability and ability. So if a person is a disabled, we cannot assume that disabled. It is not a disabled, it is specially able. So they have certain their own thinking and own way. So for specially able persons, like if they don't have legs or hands, but how they contribute to present days, how they survive in the industry, because so the Japanese cafe has introduced a robot. These persons are sitting on their home or somewhere. They can use the movements. They can talk to the like persons coming on the cafe. They take the orders. So this is the the basic of the telemetry, what the teleoperation is helpful for such a kind jobs. So how we can see that the telemetry robotics can help human beings for coming into a spatially able, for giving a bless to the spatially able persons. So actually what is the telemetry? Telemetry robotics refers to process of remotely monitoring and transmitting data between a robot and its control station or operator. It is crucial aspect of robotics system, especially in application where robot operates in an accessible or hazardous environment. Telemetry ensures real-time communication, allowing operators to track robot status, receive sensor data, and send communication for navigation and task execution. So this is a telemetry where a user or interfacer or an operator is sitting beside some place, and there is a communication channel through which it can operate the different robotic system. So overall this system is known as telemetry. So we are sitting somewhere else and we are operating the robotic systems which is placed somewhere else. So, but how this telemetry can help the robotics or this world to solve different problems. So we have seen that one problem it is solving, it can be useful for disabled or specially able persons to get their job to be done. What are the key features of telemetry in robotics? So these are the data transmission. The data transmit data in real time for robot operational parameters. Enables continuous environment monitoring through sensors like camera, lidar, infrared, chemical detectors. And second is the remotely controlled. Allows the operator to remotely steer or manipulate the robot. Crucial for unmanned systems. Supports manual override functionality in semi-autonomous for safety critical operations. Then comes bilateral communication. There should be a two-way communication. It facilitates two-way communication, enables the robot to transmit telemetry data while receiving control commands and software updates. Critical for autonomous and semi-autonomous, ensuring smooth operations. Then robust connectivity, there should be very good connectivity with both the technologies. So it utilizes communication technologies like radio frequency, RF, Wi-Fi, satellite links, cellular networks. Incorporates redundancy and error corrections to ensure consistent data flow in changing situations. Real-time feedback, there should be provided instantaneous updates from sensors and enabling dynamic decision making and obstacle avoidance. Supports adaptive behavior such as recalculating path in mobile robots, adjusting grip strength in manipulators, scalability. Telemetry systems can handle data from multiple robots simultaneously, enable swarm robotics and coordinated fleet operations. So these are the key features, data logging and analysis. So these are the key features of telemetry in robotics. So these are the features where the research is going on, and some of the features where, because there is a data lagging. So communication may be strong for data lagging. Because if you say something now and it should be responded by the robot at the same time. So I will show you some of the papers where this architecture are using with some of the different operations like schematic architecture for teleoperating a human. So that is a human-machine interface where this human-machine interface records all the human measurements like motion, speech, talk, forces, ECG, heart rate, perception. Then these measurements will come to the regulating motion reference where already feed rate motion reference are there. It selects it. Then there will be like delayed communication will be way over here, and then it goes to the robot control planner, which plans the action according to be done by the user side. Then the robot planner will plan the same action to be imitated, and this robot will give the commands to the robot to do. Like if you raise the right hand, it will give the command the robot to raise the right hand. Then there will be a sensory input that okay, right hand has been raised, so it will give a feedback through various motion and localization, technical information, then is retargeting the human feedback, then human teleoperation to visual feedback, audio feedback, or overtime feedback, or force and torque feedback. So right now, many of the operations we are working on force and torque feedback by human. Like if we tell that this any object to be a glass of water to be picked at how much force the robot hand has to pick for the glass, and how we can assume that okay, we are applying that force. So it will be a force feedback. So sensors in our gloves or somewhere which gives our a real time happening of the feedback by what the robot is doing. So it will be similar action and reaction strategy. So this is a schematic architecture that how to operate, teleoperate a humanoid robot. Then virtual reality based telerobotics. So there is always, like in the previous case, it was the telerobot which was only through the signals and everything. Right now, they introduce a virtual reality based. So you can see the 3D image of the arena, of the place where the robot is situated. So it will be like you are on that place and you are just doing the same things which the robot is doing. So it is like the framework is like that. The glove-based, they are the input devices with a glove-based controller, joystick, and a camera. Then it comes to the interaction module, a quantum converter, VR interface, utility ROS TCP controller, connector. Then from here, the target pose, the converted target pose goes to the robot hand controller, and the control commands to the robot hand. Then the second phase, like with ROS messages, with the motion planning interface and planning interface to the robotic arm, which what's the motion he wants to do. Then also the safety signals and feedback module executes the monitoring of the safety, which gives to the again the motion planning, so that if the robot is not hitting to any object or not, so it is just an obstacle avoidance system. Then all this sensory feedback through visual aids gives to the camera. So there will be a streaming of the arena which is there. So it's a virtual reality based telerobotics. So in this paper, a fundamental VR human robot teleoperation framework is integrated with gloves, hand-based controller, and joystick. An interaction interface, a motion planner module are designed enabling human operator to teleoperate a robot. Receiving feedback with potential head-ons are detected. It was a case study designed, conducted, and validated performance of the system, demonstrating promising prospects in personalized disassembly tasks. So in this case, they introduce like operator have a virtual glasses, VR glasses, and have a hand gloves, and this is the VR interface, and the robot operating scene, where the robot will do the task which the operators want to do it, and it also have the look of the task going on the scene. So it's like a virtual reality with robotics. Then how the telerobotics can be used for microsurgery. So there was a great paper in Science Journal in 2024. They tried 23 surgeries by using telerobotics for microsurgery. So here you can see the surgeon is sitting with VR glasses, and there is a micro robots which are used for surgery, and there are some assistants. And the robotic surgery assisted microsurgery combine telemetry controlled microscopes and robots unable to complete disconnections of surgeon from the operating field. So they disconnect the surgeon which are in the operating table, and he was sitting aside, and they do the 23 surgeries using Siamese surgical system and robotic scope performance. So performance learning curves and satisfaction were assessed against the conventional methods, and we can see in this graph, actually it was so small, that they all the team interaction and inoperative tumor, freedom of movement, bone neck tightness, operative comfort, these all are the performance parameters, and all are better and significantly better in that case. So the research showed that 95.7% flap survival state. It was the surgery done for the cancer, improves skill over time, surgeon satisfaction equal or better than traditional. So they assist emotional and other parameters for the team and for the surgery with this fully telemetric robotic microsurgery, and it gives that the surgeon and all can do different surgeries and with more effort, less effort and more satisfaction with them. Also, this type of surgeries can be used from afar other. If there is a great surgeon who is sitting in a different country, can operate a different machine and surgery on different place. So in future maybe they can use the telemetry for robotic surgeries by a surgeon which is placed in different countries. So in this way the telemetry also, or telerobotics, also helpful in surgeries. Then already I was talking about like feedback. So this was a paper where the combined kinesthetic and tactile feedback was observed. So this system includes a full upper exoskeleton integrated with a hand exoskeleton. The hand exoskeleton provides synesthetic force feedback in fingertips. So it will be like a force, like we observe, we have a gloves, and whenever the robotic arm touches something, so our hand will have a feedback of the force which it touches. So it's like we are feeling that we are touching something. So it's like a teleoperation with force feedback. So wideband continuous force feedback with linear tactile actuators. Sensitive force sensors at fingertip deliver clean contact and force vertical signals. So this arm exoskeleton enables tracking gravity dynamic compensation in a large workspace. Potential for fully synesthetic for entire limb. The hands, so there is a detail of the leader interface which was through a human hand, and there is a detail of the follower interface which was robotic arm. So this curves with this skeleton is veered by a human hand, and it will give the same force feedback which is follower interface is doing. So this is the experimental setup what they are done. So there the arm system is teleoperating involves two different force feedback rendering to the user. The arm and wrist like a friction and gravity compensation. The hand exoskeleton admin control, like this is your admin control. Then fingertips like open loop force. The hand position is a U-arm position control. Then from exoskeleton admin control, it gives for the Cora hand position control. Then for the fingertips, the force sensors will give a feedback to this control again. So it is a feedback system where the sensors on board on the real-time arm will give you a sensing feedback to the actuators installed on the gloves or on the exoskeleton. So in this way, the hand exoskeleton like haptic gloves supports larger, heavier mechanisms for transmitting forces to the fingers. Heavier actuator for more intense and wideband tactile feedback. The system haptic feedback quality is evaluated by measuring interaction of forces during pickup and place teleoperation task. So this was the experimental setup which we have done it to pick up and place task. So in this way, we can know that teleoperations with synesthetic and tactical feedback will give more good way for sensing that what is going on the other side. So this was the first handshake force feedback we're using with space. We're using telerobotics. Here, the European Space Agency has using the telerobotics for handshake with the people are in the International Space Station. That was the first handshake force feedback. I have seen a lots of videos from Dr. Neil Lee. Dr. Neil was Taiwanese and he is working in German Aerospace Center in ESA. So he demonstrated, he has shown me various videos where they are working on connection between the Earth and the space station. So there are many works are going on with this lab in German Aerospace Center. So they are working like for the force feedback, operating various vehicles, sitting in the laboratory and operating the vehicles far other way. They are delaying and the communication gap is analysis that how the delay can be solved. They are doing a lot of things on the various space exploration with teleoperations. Because everywhere, yeah, if you cannot send human beings to Mars or somewhere, but you can do the teleoperations there. So they are working on this fundamental of telerobotics, teleoperations for space exploration. Then, if how the telerobots can be used for schools. So I have one of the paper where if a teacher is not in the class or he is somewhere outside, how she can or he can interact with the students. So they introduce a good concept where a robot can go to the class and where she can be on the screen and interact with the students. So this is a double overview.
Double is a remotely controlled mobile teleconferencing system that enables conversations to happen anywhere, anytime. It's the ultimate tool for telecommuting. To move around, Double uses a gyroscope and accelerometer, the same concept as a Segway. It's very stable and won't tip over easily. The self-balancing algorithm will correct itself and do its best to remain upright. You can change the height of your Double remotely to match the eye level of those you're interacting with. Double also has 2 kickstands so that you can stay in one place when you need to. There's a mirror on your Double that lines up with the camera on the back of your iPad so that your second viewing angle is the ground directly around your Double. This especially helpful when navigating tight spaces. And the magnetic wide-angle lens attached to the front of your double allows you to see a whole lot more of the surrounding area than your iPad camera detects on its own.
So now, maybe next generation, teachers will be sitting in the office and there will be a classroom with double. So it's like they demonstrated this in this paper with the double, that various use of this type of systems for schools. That comes to telerobotics in industry. For interactive manipulation. So in this way, we can use telerobotics for different tasks for the industries. Where direct human interaction may be difficult or maybe in a dangerous situation. Here you can see this is for the force feedback, why the force feedback is needed. So that was all for telerobotics in various industrial applications. Now we can see that there was a good video for Jeff Bezos, the founder of Amazon, operates telerobotics.
All that roots good?
Yeah.
Thank you.
Thank you.
Help my hands.
This is a tactile favorable with force feedback.
Nice.
So that was for telerobotics. I think we can see that there was more going on telerobotics in the future. Maybe you can select one of the problems like communication delay or something for your research if you want to do some research in telerobotics. There are lots many things going on in telerobotics. So you can choose one of the feature on that and maybe work on the future. Then comes to the second part of this micro robotics. The mobile robots with characteristic dimensions less than 1 mm, known as micro robotics. So micro robotics also plays a crucial role in different ways in different application areas. Micro robotics are generally small size, less than 1 These are the micro robots developed, and red is the plastic frame, and golden is the metal part. area, but micro robotics refers to the design, fabrication and operation of robots at microscopic scale, typically ranging from millimeters to micrometer. These robots are engineered to perform tasks in an environment where conventional robots are impractical due to their size or precision requirements. The small scale operate to micro and millimeter dimensions. It are capable of precision accuracy, often designed to specific tasks with limited control due to their size. It should rely on other power sources or other control sources through electromagnetic means steering or running to external source, not by internal. You can use magnetic, electromagnetic field, chemical reactions or biological energy for making its power. So this is a concept of micro robotics. So what are the applications? It can be used for medicine like target drug delivery, like where actually the problem is there in a human part, the drug should be delivered on the same part. So it's a target drug delivery to specific cells or tissues, minimal invasion of surgeries and biopsies, micro scale diagnostic monitoring with human body, biology and biotechnology, manipulation of single cells or DNA, conducting experiments in constant biological environments, then related to environmental monitoring, detecting pollutants in air at micro level, repairing interaction with delicate ecosystems, comes to industrial applications, micro-scale assembly of components in electronics and MEMS, then for exploration, accessing constant environments inside machinery and pipelines. So these are the various applications of micro robots. Then how you power and control the micro robots. So the power sources, they use magnetic field. If you talk about external power sources, it use magnetic field, it use photoelectric energy, ultrasound, electric fields. Then comes to the internal power sources, like how you can make a power source inside it. So it's through the chemical reactions, micro batteries, biological energies, or it can harvest the energy by itself through something like solar panels, small solar panels, or some piezoelectric material. It can harvest the energy. Then what are the control methods for micro robots? It should have the external control can be done by magnetic steering, acoustic waves, optical control, electric fields. Internal power sources with swarm intelligence, like they can move with swarming of each behavior of each of them, pre-programmed tasks set with some of the sensors, or a hybrid control, maybe a control methods which can use 2 or 3 methods together. So these are the power and control sources for micro robots. Then comes to the application one by one, like micro robots in biomedical applications. They have like in the first case you can see for the delivery, drug delivery, what are the achievements and opportunities. And in the second case you can see the problems which are identified, like some of the inflammatory disease, like cancers, tissue regeneration, reproduction. So they have a micro robot designs approach for real world. The eye, brain and organs fabrication will be like shape and complexity, and the actuation through magnetic, acoustic or chemical. Then they can be implemented in the real world through medical micro robots. Then considering strategies for delivering micro robots, which are the strategies for delivering it, like through localization, accumulation and or swarming behavior. Then there should be inverse inhalation for administration, and the distribution will be used with this behavior. Then considering for selective or designing materials for the micro robots, because in the human body the material should be in that way that after using of that robot it can dissolve or it can be wave off easily. So this paper gives you an overview of what are the achievements, opportunities, and how you design it, what are the design criteria, what are the delivery strategies, and what are the how you can design a material for micro robots. There is one more, the researchers at Texas University developed a novel optical platform using holographic laser spots and optical feedback system to control synthetic swarms of active particles with unmatched precision. This system actually enables the synchronized steering of particles mimicking the natural swarming behavior of those of fish and birds. Like this platform supports the real-time adjustment of particle velocities like alignment. You can see there it can align and swarming behavior. This studies complex collective of dynamics such as this model of group of motions. So thermal manipulation with low optics power enables swift orientation of the particles. So in this way they have used an optical way to move the particle in a straight line and the swarming behavior. And this is actually not an below 1 millimeter, but this was a very mobile, groundbreaking robot which can powered solely by harnessing solar energy, demonstrated untethered motion and autonomy in various indoor and outdoor lightning and RF scenarios. So they miniaturized a ground scale which it achieves a motion with minimum energy like at 50 kilowatt using capacitor based intermittent actuation for efficient discrete motor steps. This is actually a 10 into 10 mm 1.1 gram robot can carry a payload of 3 times of its weight with only 25% speed reduction, achieving speed of 5.5 millimeter per second across a diverse surfaces like wood, concrete, soil. It can equip onboard photodiodes, millimobile autonomously seeks light, cold starts in low energy conditions, 20 watt per meter square and 10 decibel radio frequency. Like you can see the video robot.
Using small amounts of energy harvested from light or radio waves. We call this platform millimeters.
So it's a micro robot which self-harvesting energy.
To nearly 1 square centimeter. Weighing only 1 gram, our robot uses an intermittent motion approach, offering harvested energy in small steps that partially turn the millimobile. Our robot is built into 2 small motors, a carbon fiber chassis, a full PCB, and energy harvesting components like a solar cell or antenna. Our millimobile platform is also autonomous. This means it can use its onboard sensors to decide which direction to go and do things like seek out sources of light or heat. While it moves, we can also transmit sensor readings like temperature and humidity through Bluetooth at distances of over 200 meters for remote monitoring. The millimobile adapts dynamically to the available power. You can continue to operate autonomously and transmit data using as little as 50 microwatts of power. This allows it to operate in cloudy or dim lighting. Because the millimobile relies on power instead of batteries, it can operate nearly indefinitely. We hope that this work enables new research on battery-free actuators.
So this was a really mobile robots. By this I show you because how this energy harvesting is done in this type of robots. Then it was potential of how the drug delivery is done with micro robots. So that is a procedure which I can explain to you. This was a paper in the Science Journal. So it was a potential medical procedure with micro robots. So they developed a helical shaped micro robot with interlocking polymer chassis. These are the interlocking polymer chassis, and here you can see the dots. These dots are actually the drugs, which has to be sent to a particular tissue or cells. So it is made of a helical shaped micro robot with a composite material in a scaffold shape, and here a catheter. A catheter or endoscope delivers a micro-robot to the body or region where it was to be treated. So micro-robot assemblies are deployed and navigated through electromagnetic navigation and which can be sent to other parts or the tissue where it should be in a place where there should be a place or a target where it has to be dispensed. So these micro-robots disassemble and release therapeutic agents. Then the micro-robots are degraded and then absorbed or cleared from the body. So this is the material which can be absorbed by the body. So it navigates through the assembly and the drug is released and the clearance and degradation of the clearance when the drug after degradation of drug to the tissue. So this is the system where the micro-robots can be used for the drug delivery. This is a procedure for the drug delivery, and these micro-robots after the drug delivery it degrades or dispense in the and absorbed by the body. It will be non-harmful, but it's made of non-harmful materials, and it can navigate through the electromagnetic navigation from outside the body. So this is actually the drug delivering concept with the micro-robots. So that was all about the micro-robots. Then we can have a 10-minute break. Then we go for space soft robots. Okay? So after 10 minutes, we'll start with space soft robots. So I was very curious because my background is aerospace engineering. So I was too curious about soft robots when I came here in Taiwan 3 years back. I've seen soft robots, how to manipulate it. Then I've seen the research done by NASA for making space soft robots. So I was very curious on this topic, space soft robots. So there is a documentary by them.
There's a lot of things that you need to do on the surface of another planet, such as exploring a site or maybe correcting an instrument or creating a temporary shelter to shield from dust or wind on Mars. We are looking into a swarm of soft robots that can move around the surface of another planet and then link together and create these temporary structures or do various tasks that we need them to do.
Right now, what we're focusing on is some different properties for these soft robots. We've been using silicone by 3D printing molds pouring the molds and then peeling out the silicone from there. And we've been able to make different pneumatic networks within the silicone so that when they're inflated, we have different types of actuation. So we're investigating these different properties so we can think about, okay, what would this look like on a lunar surface or a Martian surface? Some of the advantages for soft robotics are that they're very compliable, so you can twist, hammer, and then they still work. Soft robotics are good because they're compliable. They deform and can hold these objects better than a traditional robot, which is very rigid.
This is important because soft robots are extremely resilient to damage, and so they can be used for a lot of things. And if they're able to move around and create structures in different locations, they can create a structure, break down, and then move and create another temporary structure. So there's a lot of reusability factor with this.
So this was the video which I've seen from the NASA, and I've searched many of the exploration which they are working. So because for the space, it's another planet exploration. We don't know what type of surfaces that in that we have not seen it in proper way. So many of the traditional robots may be damaged or have a non-working. So there is a new era of space soft robotics. So here the space exploration is a profound vital enabler that expands or understands the universe of origins of life. They have recent missions like Mars rover, Perseverance rover, which is a crucial role in space robotic technology. So what will be the role of space robots? So it just poison in dispelling future space missions. Traditional space robots with rigid structure face some limitations in the terms of adaptability. So the advantages of the soft robots will be it can possess a high degree of flexibility, adaptability. It is due to their robustness for various space applications. Their ability to navigate complex and unstructured environment shows the distinctive advantage for the space robots. But yeah, there are some challenges and opportunities like low gravity, vacuum conditions, extreme temperatures, radiations. So research in this area infinitely holds a great potential for future space exploration. So here you can see the prospects of future space like soft jumping robot for surface exploration, browsing of soft robot for surface exploration, soft gripper for the rovers, soft crawling robot for surface exploration like flapping aerial wheel for aerial resonance. So soft robots for on-orbit missions, foldable solar cells, implementable antenna. So these are the prospects of the soft robotics in space applications. So what are actually the requirements for space and characteristics? So first requirement is microgravity. So spacecraft experience generally partial weightlessness, leading to unique mechanical effects, challenges in modeling, control due to different motion behaviors. So they get like microgravity, extreme low temperatures, ultra high vacuum, maybe in some parts they got the extreme high temperature, solar winds, high energy radiation. So these are the issues which space robot has to sustain. So space environment challenges, material adoption, manufacturing precision, adoption of actuation, enhanced sensing and control. So these are the specific requirements of space soft robot. So how you design it? Designing a lightweight, flexible robots for space mission is complicated due to non-linear material multiphysics field coupling. Nature-inspired designs will simplify the process. Biomimetic methods can be used for manual design. Various optimization methods such as analytical strain energy, density functions, finite element analysis, topology optimization. Evaluatory algorithms can be assist for automating designs. predictive layer designs, adaptive mechanical properties enable precise, forceful and compliant interactions with space environments. So soft robots exhibit complex, non-rigid dynamics with stronger non-linear effects, making accurate modeling challenges. Constitutive models of soft materials provide the basics of understanding of soft kinematics. Kinematic modeling of soft structure should be considered for large deformations and is described in models like piecewise constant curve, PCC model. These are the basic of how to design it and what are the prospects for modeling. So various soft material can be used for space exploration. So I have highlighted some of the materials which can be used for the space applications. So there are special requirements like temperature, radio resistance, anti-corrosion, high strength and self-healing properties. So these are the existing materials and this should be the potential materials for them. Now comes to the fabrication techniques for space robotics. Like it's a space soft robotics. So it's the fabrication technique is similar to the soft robots. This space is a word which is an application area. So we can use stereolithography, selective laser sintering, injection molding, which use soft polymers, transfer printing, lamination, manufacturing, soft lithography, direct ink writing for aerogels, and soft lithography and lamination manufacturing for smart materials, fused deposition modeling FDM for hydrogels, and ink printing. So fabrication of soft robots can use these of the additive manufacturing techniques, including other techniques like injection molding, and the material can be used as hydrogels, rubbers, soft polymers, smart materials or aerogels for the fabrication of soft robots. How the actuation can work? So there are two types of actuation can be used for soft robotics. One is the fluid actuation. The soft robot can use hydrostatic pressure force for motion. The second actuation is the smart material actuation by smart material like piezoelectric, thermally responsive to light, responsive material to actuate the soft robots. Then second part is you can use chemical actuation. Soft robots use chemical reactions to convert fuel-based chemical energy to mechanical for movement. So actuation of the space soft robots can use physical actuation or chemical actuation. Then there should be the selection of sensors and controls for the space soft robot. So it should be a model-based control or model-free control. So if it is a model-based control, it uses the kinematic models like PCC for microgravity environments. Non-constant curvature models consider for external loads, machine learning aid modeling. Space conditions have limited impact on this model-based control. There should be a model-free control suitable for complex, uncertain space missions, which outperforms model-based control in some cases. Behavior-based control like human-machine interfaces. So this is the potential sensors for space robotics. We can use carbon nanomaterials, materials like hydrogels, which have a self-healing property or adaptive property or a multi-scale functionality. We can use wireless communication, degradability, temperature resistance, shape adaptation, easy integration and easy attachment. So these are the properties which we should be considered for developing sensors and controls for space soft robots. So what are the potential space application of soft robots? So soft robots are on-orbit missions. It can be of use for foldable mechanisms for lighter spacecraft components, robots for space section maintenance, planetary exploration, soft gripper for debris removal or versatile operations. Soft robots for planetary exploration can be described and used for flexibility and robustness for harsh planetary environment. Aerial exploration with flapping wing. Soft robots for mobility, digging, exploration in changing terrains. In flammable and impact-resistant soft robots for planetary surface use. Then soft robots for deep space exploration, use of aerogel composites in deep space equipment. Soft robotic structures for Mars rovers, spacecraft. So these are the potential space applications where we can use soft robots. Now, what are the industrial applications for the soft robots? So there are various industrial applications. So one of the applications which I can show you, it's like for inspection. How these small tiny robots can inspect. Like from starting slide, we have seen that in micro robot it can be used for drug delivery and all. So here the space robots can be used for inspection.
It goes without saying that it is very important for airliners' jet engines to be regularly inspected. Such inspections could soon be easier and more thorough than ever before, thanks to a robot that moves like an inchworm. Currently, inaccessible parts of jet engines are imaged via borescopes, which are essentially long flexible tubes with a video camera on one end and an eyepiece or screen on the other. The force of gravity often causes the camera end of such devices to droop down unless braced against an engine part. However, plus it can be difficult to maneuver the camera deep into the engine. That's where SensorWorm is designed to come in. Its name and acronym for Soft Electronic Skin Innervated Robotic Worm. The bio-inspired soft robotic device is being developed by a team of GE Aerospace research engineers working with colleagues from New York's Binghamton University and Ohio-based research and development organization, UBS Incorporated. After being deployed into the turbine inlet or exhaust port of a plane's engine, the compact robot is able to make its way through the engine via an inchworm-like push-pull style of locomotion facilitated by vacuum cups on its underside. As the bot does so, it transmits live video from a forward-facing spotlight-assisted camera, imaging any cracks, corrosion, or other problems it may encounter. Importantly, though, SensorWorm doesn't just provide video. Sensors on the existing prototype are capable of sniffing out gas leaks and measuring the thickness of thermal barrier coatings on engine parts, with other sensing capabilities currently in the works. Down the road, it is hoped that the robot could even be used to perform remote control repairs. The final version of the device should be completely self-contained and untethered, housing its own power supply, microprocessor, and other electronics.
You can see this is the paper also available in the web. It's called a SensorWorm. So they develop a space robot of the behavior of an earthworm, the behavior of the earthworm for various inspection tasks, and various sensors are mounted on the soft robot so it can be moved easily through the part which is like you have seen in the gas turbine engines are very big engines. When it is compact and you have to inspect inside, so it's impossible to get it to inside and you have to or you have to dismantle it everything. So these are the space robots can be moved inside and check whether everything is fine or not. So this application, this type of applications may be an industrial part of the space robots, soft robots. And soft robots, in our lab also we are working on soft robots for climbing the wall so that it can stick to it with a vacuum or suctions. And we are also imitating behavior of different animals so that soft robot can be developed by imitating them. So there are many applications in future made possible with this soft materials and soft robotic development. Due to the development in additive manufacturing, it is easy to fabricate it and it can be retrained and you can make n number of soft robots easily. So all of these three phases which we have seen. So there are major challenges we have come across into the robotics. The first one is the adaptability. Robots struggle to memorize the learning tasks across different environments and applications. There are no robot which can learn itself through different performance or different environments. So there is an adaptability challenge across the robotics. Ease of programming, like traditional programming method requires expertise, making robot programming inaccessible to non-specialists. So how there should be a method which can be ease for the programming. human-robot interaction, teaching robots through demonstration, natural communication is still limited. So there should be a more focused way where human-robot interaction should be in a more scalable and easy way. Then the cost and scalability, custom programming for specific tasks can be inexpensive and time-consuming. So there should be the modeling way or the simulation way where the cost scalability can be done on a smaller scale and cost can be reduced. So these are the major challenges across robotics. So we are thinking that which challenge can be taken care of with using. So right now everyone knows about the large language models. So there are many large language models which are day by day coming into existence and making very where you can ask something into it, it can just a text generated for you without any interaction. So how can robotics benefited from these large language models? So there is another way with transforming the future robotics with multimodal LLMs. So here we are taking care of many aspects or many challenges which can be overcome through transforming the robotics with multimodal LLMs. Let's see that what is in the past and
what do you think of when you imagine a robot? Is it this or this? Robots have come a long way in recent years, but they're still far from being able to think and act like humans. This is because they're only programmed to perform specific tasks, or they learn from demonstrations, which makes them inflexible and unable to adapt to new situations. But what if there was a robot that could learn and adapt on its own? A robot that could understand the world around it and take action based on its own understanding?
In this video, we have seen that there are whatever challenges we discussed are the same with what they are talking about. Like how we can just make a robot which can just imagine from the surroundings by seeing you, like okay, what should be the next or what can happen to that. So like existing, we have a problem. It's the project which we are already doing it. So we have a human-machine collaboration. We have obstacle avoidance, human motion recognition, stereo vision. So this is the existing robot-human-machine collaboration system. But what will happen if the humans can talk to the machine that, hey robot, take tool A and fix the item X on the workpiece when I finish my task of screwing on the workpiece. If I say something like that, how it can be possible that robot, because current robot you have programmed for certain tasks, certain applications, how it will change. So this is the existing problem which we are having. So how this futuristic multimodal LLMs can help us to build a new generation of robotics where it can, with artificial intelligence, can think of and reprogram itself. So there are large language models which are used for text generation, classification, knowledge answering, translation, dialogue generation. There are OpenAI, Core, Bloom, Spare, Meta, Lamb. These are the various large language models according to the functionality. So how the LLM can be used in robotic affordances? Like large language model have supervising ability to reason and decide under common sense. Suppose, how would you put an apple on the table? If you ask a robot or you demonstrated this work with natural language processing, so how it works? So it goes to the LLM. Then this large language model have combining options. So it has a find apple, find coke, find a sponge, pick up apple, pick up a coke, place the apple. Then it should be giving certain value functions for all these codes. So it gives a various options. So if you ask what will you find, how would you put an apple on the table? The first one is, so first is the apple. So there will be a find an apple. So there will be certain skill affordances using policy network and value network to evaluate the proposal. Your proposal is to put an apple. So it will find the values, functions for all these combined options and give you that find an apple as your first function. So it will calculate the first function for finding an apple, then it process and it comes to the table, so finding an apple, and there will be a second one. So they will be take action step by step. So in this way the LLM can be used for robotic affordances that we can use to give a prompt, and we can combine it with separate value functions. So this is a framework for proposed GPT-4 empowered for task planning. So they have, like in this case, in this paper, what they have done is they have a demonstration video, and there will be an environmental instruction that pick green chip bag from bottom drawer and place on the counter. So here there will be a predefined action pool like moving hand, grasp an object, release an object. So the GPT will make a plan with using predefined action pool and your instruction and environment together, and this GPT-4 will generate the plan step by step, move hand to the location, grasp the target, move hand to the target, and release the target on the counter. Then there will be action plan generated with predefined action pool, and these action plan and then in this paper what they've done is they have matched with the demonstration that the matching score is same. When the matching score is same, the target is to be done, or if matching score is high, it can just generate and exploit this action plan to the robot arm. So it will work according to the robot arm. So it will generate an action plan which you have instructed it through the large language model like GPT-4. Then there is another paper which they use a program prompt for planning. The program prompt is an Pythonic code they made for the planning. So they may import some action primitives, they import some available object list, and there are example tasks they already put for the program prompt for the planning. Then with this prompt, the LLM will generate the plan. This plan, when there will be a state feedback that if this plan is not actually with or there have some issues or false, there will be again the feedback will be gone to the element, and the generating plan will be again regenerated with this. And the example for the decision check is there. They put some prompt for state feedback and examples where they will get the decision check, and then it will full execute. If everything is fine, then current schematic, then there will be execution of the plan. So in this way they use the generative situation using program prompt for task planning or using large language model. You can see this program, all these codes, and you can want to try. That is available in this link. You can see that sorting the fruits, put a banana in the table, they put this. So it is the robot is doing the same things with the task plan, different task planning. So no need to program for specific applications. So using large language model, we can reprogram the robot through certain instructions, and it can follow different tasks without making a single task problem. So first they simulate this one, and then they go through the sorting of this robotic arm with an experimental setup. So in this case, they simulate it with bringing a coffee cup toy on a coffee table. So this was a good paper for generating LLM using program prompt There are various other methods also they use. Because of the program prompt, the task will specifically align to whatever is being fed to the system. So for the closed environment, it gives a good results. So now you can see the solution, which if there is a role, they are asking for the tool A, the program prompt for the planning, and there will be the natural language processing where speech to text has been converted, and it can generate a plan, and there will be a accession check for the convert environment, and the large language model will execute the final plan, and the robot will ask the human that, hey human, I have saved tool A and going to start fixing the item X on the workpiece. Kindly say yes if you don't have any other query. So it will be a feedback system where the robotic arm will give you a feedback that, okay, I finished this task, I was trying to start this task. If you say yes, then the task will be performed. So its final execution will be like that. So this is our, I think, project which we are doing it in our final year of the proposal. So this was the 4-year project, we just completed it, and this is the last year for that. So what's the role of multimodal LLM plays in the evolution of robots? So multimodal LLM significantly enhance machine intelligence, enabling robots to evolve from single-purpose machines to general-purpose systems, capable of analyzing, reasoning, learning. The shift begins scalability, reduce the cost, wider adoption, kind to general-purpose platform like PCs and smartphones. So in this same multimodal role, Tesla advancement in robotics from Bumblebee to Optimus highlighted rapid progress in humanoids. So they use large language models to develop their design of equipment from 2002 to 2023. So in this way, if you use large language models, there is a cost-effective solution for changing or adaptability of various designs. So humanoid robots can be also developed for 3D work like 3D generation done in healthcare, educational, hospitality, robots like Boston Dynamics, spot case interactive capabilities, such as acting museums, demonstrating potential for dynamic engaging applications. So there are various role of multimodal LLMs for the evolution in new generation robotic systems. Now what are the robot transformers? So robotic transformers which translate multimodal input into action and rapidly evolving. So there are some platforms which are the transformers which uses, if you put these transformers into application, it will be, it transforms your actions into rapidly evolving. Like if they see something, then they already imagine that what's going on behind the scenes. So it's like the Google DeepMind RT2 performs equally well as RT1 with 100% success. So they have emerged from the vision that if there is a bottle full of water, so in the image, in the transformer sees that there is a bottle of water. So what will be the next steps? They will mean that the bottle, maybe the bottle is full of water, full of something else, bottle is of blue color, red color. So the image and transformation, it has their own capacity to understand it with various functionalities. So Microsoft also introduced the large language and visual assistants, and Google DeepMind AI they are the robotic transformers. Tesla moved into humanoid and robotic field with significant, not only but in design, scale and production. So Tesla's autopilot strongly full driving technology foundation can leverage to robotics. So that's what we are starting. We have in the first video, what we have left was just what to do. So in this, we can find out what they have done.
That's the promise of Google DeepMind's new visual language action model, or VLA, called RT2. This model can help robots to translate visual inputs and natural language commands directly into robotic action. And this will prepare robots for unique situations that they couldn't experience during standard training patterns. RT2 can learn to perform new tasks simply by being told what to do. It can also learn from its own experience, adapting its behavior on the go. For example, if you ask it to pick up an apple, it will do so by reading or hearing a command in our natural language. We're going to take a closer look at RT2 and its capabilities. We'll see how it works, what it can do, and most importantly, what it means for the future of robotics. DeepMind has been working on RTX models for some time. Their first release was the RT1 model at the end of 2022, which was trained on large-scale data. They trained 13 robots over a period of 17 months, collating demonstration data, which showed a 97% success rate for this model. Then came RT2, which is a VLA model that can process both visual and linguistic information. The VLA models are trained on massive data sets of images and text, which allows them to learn the relationships between objects, actions, and words. Once a VLA model has been trained, it's then able to answer questions about images and videos, translate between languages, and perform robotic actions. VLA has three main parts. The first is a visual input system that takes images from the robot's camera and extracts features such as object shapes, colors, and texture. Then the natural language processing system takes language commands as inputs and translates them into sets of instructions that robots can understand. Lastly, an action planning system takes instructions from a natural language processing system and generates a sequence of actions that the robot can take. In simple terms, RT2 works by translating visual inputs and natural language commands directly into robotic actions. Let's break it down with an example. If a robot's camera captures an image of a table with a cup on it, the visual input system would extract features from the images such as distance, shape, or the color of the cup. Then, when a human asks the robot to pick up the cup and place it on the counter, the NLP system would translate this command. As a result, an action planning system would generate a sequence of robotic actions, such as moving the robot's arm to the cup, holding the cup, and moving it to the counter. The robot successfully performs this task based only with a voice or text command that was given in English or any other language. So how could the RT2 model be used? How could it benefit mankind? Google DeepMind released a paper that highlights many interesting use cases for RT2, and the results were incredible. RT2 can pick up and place objects of different shapes, sizes, and weights. It can also hold objects in different ways, depending on the object's shape and orientation, just as we humans hold a plate differently than a cup. RT2 can also navigate through an environment that's cluttered with multiple obstacles. Previous generations of robotics would get confused in a situation like this because they weren't programmed to handle unexpected scenarios. It can also make decisions based on reason. Since RT2 has access to web-based data, it'll use that data to acquire knowledge and concepts that help it to reason and take the relevant action. For example, deciding which drink is best for someone that's tired. RT2 would reasonably recommend an energy drink by learning that energy drinks contain caffeine and that caffeine can boost energy. It can break down problems using logic and come up with a solution. As an example, using a rock as a substitute for a hammer. In the absence of a hammer, RT2 can figure out that a rock is also hard and heavy and would do the job. And you can talk to RT2 just like you would with Siri, Alexa, or any other AI assistant. The big difference is that now you'll get a response in the form of an action. So if you ask it to go to the kitchen and get a glass of water, it will do just that. These are basic examples, but imagine the possibilities. Humans could delegate household tasks to robots, giving us more free time. Or in the education sector, imagine robots teaching science or history, using natural language and visual aids. And imagine how life-changing this could be for those that can't function independently, or the elderly in need of specific care. In hospitals and nursing homes, robots could help patients get in and out of bed or deliver meals and medication. If robots could perform the tasks of humans, following verbal instructions and using independent thought, logic, and reasoning, it would change the world forever. Of course, it's early days, and these robotics models are still under development. They've not yet been tested on a large scale or within commercial environments. And there are still many questions to be answered on the subject of regulation. Who's ultimately responsible for the actions of these robots? How do we ensure that they're used for good? And how will we prevent robots from becoming too powerful? but it's safe to say that sci-fi is becoming reality.
So it was the future with Google API and what the question we have asked that how robot can be used. So with this vision-based large language model and multimodal LLMs can be helpful for the future generation robotics. So maybe, do you know who said this? Anyone?
Elon Musk.
Yes. It was Elon Musk who said that in the showcase of Optimus Generation 2. So these are the humanoid robots. They think that in 2040 there will be more humanoid robots, and with $30,000 they want to sell it to anyone. But what's next? How we can cope up with that type of category? So it was a good quote with robots inherit the earth. Maybe yes, they will be optional. So thank you for listening, and we can work for this 17 sustainable goals for future. Thank you. Any questions? Any discussion? I put a lot of slides and a lot of videos for that maybe for the showcase, so it may be interesting. Like the last project we are working on with like human-machine collaboration with large language models input. Also, there is a book chapter which I will share you regarding chapter which is going to be released by this month. In the book for cyber's physical approach for various robotics by Professor Yang Peng Shen from University of California, UC Merced. So this is our chapter which we focus on various positioning system, like for errors, which are the various type of errors in the robotic systems and how you can compensate it. So this is the basics of that and how you can compensate it with different cyber-physical approach. So maybe you can, there you can see that there are various types of error. It was a workspace dependent error or geometrical errors. Maybe it was a non-geometrical errors, the tasks and system dependent errors, and various robotic absolute positioning and compensation through different cyber-physical system approach. So here you can see that what is how you can compensate that type of errors. So there are how to measure that errors first and how to compensate it. So there are different measuring instruments like laser tracker, 3D printer, 3D positioning using cable encoders, theodolite, wireless positioning, stereo vision. So you can just go through it for the basics. As you are robotics students, maybe this chapter can helpful to get to know about various error positioning and compensation. So here you can just know about what are the laser ball, theoretically, how acoustic errors are there. Then you can model the error, how you can model the errors. overall modeling of positional errors, then compliance error modeling, then cyber-physical based correction of positioning of errors, then neural network based error compensation, then using vision based error compensation using active markers. So we already work on vision based error compensation using Aruko codes, which is the paper is in under review. Then path planning and obstacle avoidance with cyber physical robots. Then how we can use the common envelope methods for that. So you can use like Newton's method and gradient descent for gradient minimization for various path planning optimization. So this is a book chapter which maybe I will share to the PA so that it can be given to you. So here you can just know about the errors and its compensation. Okay, thank you. So this book chapter I will share you the TA, maybe you can it may be useful for you to know about the errors and its compensation. Thank you very much. Anything else?
Like I have a question. If someone is coming from another background and wanted to explore in robotics field, from where he should start? Like what the basic thing?
This is a generalized question as it's same as me because I come from the aerospace background. Then I was working on drones, so I have an interest in aerial robotics first. Then after coming to Taiwan, I was interested in various industrial robots. So it's just you start from the beginning. Just start with a small. Maybe you can make a small autonomous robot with a small Arduino and just program it, just move it. It's starting with that.
Before going to hands-on, we should learn something basic like water sensor and this thing.
Yeah, you can use you can learn the kinematics of mobile robots, basics. It will be beneficial for you. Anything else? Thank you very much for listening me. Thank you. Anything more to say?
So thanks Dr. Lau for a very nice speech. And so we will be going to Ireland for next week. So next week is 10:30. So where will we go?
I will put the information in the Facebook group.
Okay. So next week we'll go to Ireland and Taiwan. So if you are interested or if you are participating in these trips, so you can check with the Facebook group for further information. So that's